this is Mrs. Nyman. We're on Unit 7.6, I think it's 6, which is on the strength of acids and bases. So we've talked about this a little bit, but we haven't gone particularly in depth with it. So the strength of an acid or a base depends on how easily it can dissociate completely in water. So if you have a strong acid, that means it can dissociate all the way. 100% of the acid molecules will dissociate into their ions. So right now I have this written as an equilibrium expression with the double-ended arrows. But really, if I'm saying that every single molecule splits up into the ions, what I'm really saying is all of our stuff is going to end up as a product. So when I'm talking about equilibrium, I'm going to be able to say that this has a high Ka, meaning that we exist more as products than as the reactants. So this is also called product favored. And remember that the equilibrium constant, or Ka, just tells me what do we have a higher concentration of? Do we have a higher concentration of products, or do we have a higher concentration of reactants in our equation here? So when we have a strong acid, have way more products because we end up with a whole bunch of ions. So really, when we say something is a strong acid, what we're saying is that it's really good at donating hydrogen ions. It donates all of the hydrogen ions it possibly can. So it's very, very good at acting as an acid. That's why we consider it to be a strong acid. Now, there are 7 strong acids that you need to have memorized, and I'm going to list them out here. You need to have them memorized for your test. So these are your 7 strong acids: hydrochloric acid, hydroiodic acid, hydrobromic acid, sulfuric acid, nitric acid, HClO3, and HClO4. You need to have these memorized. Anything that does not fit in this category that is still an acid, we would consider to be a weak acid. So these are the only strong acids. Everything else that is an acid is a weak acid. So strong bases, we say, can dissociate hydroxide ions at 100%. So let's say we have NaOH. Oops, sorry, shouldn't have moved that. Colors. Okay, let's say we have NaOH, and then we've got our equilibrium expression here. Because it is a reversible reaction, we're going to split up into the ions of sodium ion and hydroxide ion. So we are saying that 100% of the sodium hydroxides split up into their ions. And remember, if we get a lot of these, they are going to steal the hydrogens from hydronium ions that are already in water, and they are going to lower the concentration of hydronium ions, which increase the pH. Now, strong bases are really good at being bases. They're really good at producing those hydronium ions or hydroxide ions because they produce as many as possible when they are strong bases. So again, we are here talking about having a very high Ka because we are, I don't know what's going on with my colors. I guess we're not going to use black again today. I don't know why I can't get another black color. But when we have a strong base and a high Ka value, it's a Kb value now because we're talking about bases. That means that we exist product favored again. Product favored. We are lying mostly on the product side. We are making a whole bunch of the ions. That's what that Ka value means. So we do have some more strong bases that you need to have memorized, and I will put those up right up here. So these are your strong bases that you need to have memorized. Really, instead of memorize each individual strong base, I would memorize these rules here. So if we have an alkali metal hydroxide, that is any metal in group 1 with a hydroxide ion, it's going to be a strong base. Lithium hydroxide, potassium hydroxide, sodium hydroxide, and rubidium hydroxide. For the other one, I can't spell apparently, it's alkaline earth metals, hydroxides, but only the heavy ones. Anything heavier than calcium, so calcium, strontium, barium. Those are the ones that are going to be most used as our strong bases that you need to have memorized. These are the ones that dissociate completely into the hydroxide ions. Okay, so here we have our weak acids and bases. So the weak acids and bases generally only dissociate about 15%. So let's do an example here. Let's do acetic acid. CH3COOH plus NaOH. Okay, it's going to make sodium acetate. Oops, no minus sign. And water. Okay, so the problem here is that this acetic acid is a weak acid, so it's not going to dissociate completely. It's only going to give off about 15% of its hydrogens. It's only going to split up a little bit into its ions. So what that means is that the acetic acid isn't going to be all the way over into splitting up into ions. So what's happening with the acetic acid itself, we have something that looks like this. H3COO minus plus H plus. Okay, but with the acetic acid, it's a weak acid. It is not splitting up into ions very well. It's mostly staying as this reactant. It is not splitting up into the ions. Therefore, this hydrogen here is not being donated over to the sodium. It's not doing a very good job at being an acid. So we say that considering most of it is lying on the reactant side, we are staying mostly as our reactants, we say that weak acids and weak bases have a low Ka, meaning that, or low Ka or low Kb if it's a weak base. This means that it is a reactant-favored reaction. It's not splitting up into its ions as well. Favored. Okay, let's talk about how this applies to the titrations that we did yesterday. So yesterday we did a strong acid, strong base titration where the moles of acid equal the moles of base at the equivalence point. That's true all the time. The moles of acid equal the moles of base at the equivalence point. And when you have a strong acid and strong base, the pH at the equivalence point is going to end up being 7 because they're going to neutralize each other right at 7. It's going to be perfect. But when we have situations like this, where we have a weak acid and a strong base, it's not going to neutralize at 7. Let's kind of look at a pH line here. Okay, pH of 0, pH at 14, pH at 7. So we have a strong base that's starting over here at a pH of 14. And then we have a weak acid. So that weak acid already gives up fewer hydrogens. So since it's not going to produce as many hydrogens because it's not splitting up into ions, it's not going to have as high of a concentration of hydronium ions. So weak acids end up having a lower concentration of hydronium ions, therefore a higher pH. So let's say that this is a weak acid. It doesn't have a super low pH, again, because it doesn't create as many hydrogen ions as strong acids do. So when we have a titration between these two, it's not going to meet in the middle at 7 because there are fewer hydrogen ions here. Fewer hydrogen ions here for the base to actually neutralize. There's not as many. So when these guys meet in the middle, they're going to meet in the middle somewhere in between. Now the actual calculation you need to do to figure out what the exact pH at the equivalence point, you guys aren't going to do in this class. We could do this titration with pH probes, we could graph it and figure out what that point is, but it doesn't particularly matter what that number is as long as you understand that the equivalence point, equivalence point of a weak acid, strong base isn't going to meet at 7. It's going to meet a little higher than 7 because we have more hydroxide ions than we have hydrogen ions. So we're going to end up on the base side of the pH scale. Now, when we're picking our indicators, this is going to be really, really important. Yesterday, we used an indicator, phenolphthalein, that indicated a pH around 7, which was perfect when we have a strong acid, strong base that equalizes or has the equivalence point at 7. But in this case, we don't want the indicator to be phenolphthalein because phenolphthalein changes colors too early. So this is that thing that we talked about yesterday where your end point, when your indicator changes colors, and your equivalence point need to be the same. So in this case, we would need to know what the pH is going to be at the equivalence point, and we would need to pick an indicator that does that. Some indicators change color at pH of 7. Some change colors at pH of 2, 4, 8, 10. There's an indicator for just about every pH. But we need to make sure that we understand that when we have a weak acid and a strong base, or vice versa, the equivalence point isn't going to be at 7. And we need to pick an indicator that works for that new equivalence point. Otherwise, our titration calculations are going to be screwed up because the indicator is lying to us. We don't want the indicator to lie to us. Okay, the other thing that's really important here is when we're doing our dissociation calculations. Last class, when we solved for pH using negative log of hydronium. Okay, but the problem is that this hydronium concentration, yesterday we were like, oh, cool, the concentration of the acid is 0.01 molar, and we were able to plug that number right in. But that only works, first, if the hydrogen or if the acid is monoprotic. If the acid only has one hydrogen, then we are able to assume, and if it's a strong acid and monoprotic, then we can assume that the concentration of the acid is the same as the concentration of hydronium. But the problem is that's not always true for every single thing. We have some strong acids like H2SO4, but H2SO4 splits up into 2 hydrogen ions. And when H2SO4 splits up into 2 hydrogen ions, it's not a 1-to-1 mole ratio anymore. So if I have a 0.02 molar sulfuric acid, I can't just plug in 0.2 for the concentration of the hydrogen ion because that's not true anymore. So what you do, if you have a strong acid that is polyprotic, meaning multiple hydrogens, you have to multiply by the number of hydrogens. So we have 2 hydrogens, therefore our concentration of hydronium is 0.04. So then you can plug that in, negative log of 0.04. So anytime you can do the same thing for a base. If you have more than one hydroxide or if you have more than one hydrogen, you have to make sure that you multiply. Now this only pertains right now to strong acids and strong bases that have more than one hydroxide or more than one hydrogen. You are going to make sure that you always multiply them so that your mole ratio is correct and you can figure out the accurate form of your hydrogen ion. When we have a weak acid or a weak base, we need to do one extra step on top of this. So I forgot completely to tell you what the actual answer was, but the reason why this is important is because when you're doing your pH calculations, you need to have the correct concentration of hydronium. Not the concentration of the acid, not the concentration of the base, but the concentration of hydronium, or if you're doing the pOH calculation, the concentration of hydroxide. So make sure that you do pay attention to if it is a polyprotic or a polyhydroxide acid or base. Now, for the weak acids or bases, you need to be given an extra piece of information. For the weak acids or bases, let's say that we have HF. HF is a weak acid, and I'm making this up as I go along, but I'm making up that HF has a dissociation of 10%. Okay, so that means that hydrofluoric acid only splits up into its ions 10% of the time. So let's say that this is a 0.25 molar hydrofluoric acid solution. So before I can figure out what the concentration of hydronium is, I need to multiply the 0.25 times this as a decimal. So this is a decimal turns into 0.10, because only 10% of this solution splits up into its ions. And I have to give you the dissociation percent, and I would have to give you the concentration of the acid or the base in order to do this. So 10% of 0.25 is 0.025, and that is your concentration of hydronium for this weak acid. And you do this every single time if you have a weak acid or a weak base. And it's kind of easy to tell which ones are weak because I have to give you the dissociation constant if I expect you to do this calculation. So at this point, we have talked about what a strong acid, strong base is, what a weak acid is, how they will impact each other when we do a titration, what happens when we have a weak acid, strong base, or a strong acid, weak base titration, how that affects the equivalence point. We talked about why it's important to pick a correct indicator, and now we are discussing, or now we finished figuring out the concentration of hydronium or the concentration of hydroxide for polyprotic and polyhydroxide ions, and we were able to figure out how to use the concentration of hydronium for a weak acid or weak base. From here, you could then plug it into the pH calculation and do that. Okay, you guys have now learned every single thing for this unit, and your test is on Friday, next Friday. So make sure that you guys are coming in for help if you need it. We will have some time to do some practice and all of that. But make sure that you are doing some practice with this. This is not something that you can just study by memorizing. So the pH of this guy is 1.6. pH equals 1.60. Yep. Okay, you guys have a great day.